things when I don't want it to log me out. It's a little rude. Okay. All right.
Oh, yeah. They both like that.
All right, so let's go ahead and talk a little bit about some of the words up here, some of the things. So we actually have two different types of series, and one's a little bit silly. The first one is a Taylor series. It's named after an English mathematician named Brooke Taylor. So essentially, I want you to think of this as like an extended tangent line. So a tangent line is really good at approximating near a certain point. Usually we call that point the point of tangency. And we match the point, so the y value, and the first derivative. What a Taylor series, or in this case, a Taylor polynomial, because we're going to end it at some point, is going to do is it's going to start matching more and more derivatives. So we're not only going to match the first derivative, the second derivative, but however many derivatives it asks for. Now, we have specific names for where we write this Taylor series. So that C, it's in a lot of the places. This is going to be called our center. So this is like the x value where I ask you to write your tangent line, or in this case, the x value where I ask you to write your Taylor polynomial. What you kind of noticed in the video that we watched, and if you can see, and I can show you more next time if you're interested, is that each one of these terms is specific about one derivative. So like this term, make sure I match the y value. This one, make sure I match the slope. This one, make sure I match the second derivative, third derivative, and so on. Yeah, Brandon.
Did you say that C?
Yes. No, all of those C's stand for center. So whatever we're centered at is going to be a really important point to our graph. It's what we're plugging into all of our functions, all of our derivatives, and we're going to see x minus the center in all of our terms. Yes. Yes. So it'll say something like centered at x equals 2 is what we're going to use for our first couple of examples. But kind of analogous to that where we wrote the tangent line. So that x value where we wrote the tangent line, we're just extending that idea of a tangent line to match more and more derivatives. We call this guy the nth degree Taylor polynomial. So whatever our biggest power is the degree. Kind of the same thing as when you did polynomials in algebra 2. Your degree is just your highest power. Now, we're never, ever going to multiply the stuff out. So when you see those x minus c's, that point, that x value is really important to us. So we're going to always leave those relatively unsimplified in terms of what we would look at. All right, question. There was this Scottish dude named Maclaurin. He named this after himself. What's the only difference between these two? C is 0. So notice all of the x minus c's are now just like x squared. So the funny story in my head, I'm pretty sure this is not how it happened, is that Maclaurin was like, I see your work, Taylor. I'm going to plug in 0 and I'm going to name it after myself. So literally the only difference is that the center is 0. You may be asking, why would you tell us that? It seems like an extraneous piece of information. The only thing you're going to need to know is if I tell you to write a Maclaurin series, then I don't have to tell you what the center is because you should know that the center is 0. So that's just a crafty way for me to tell you that the center is 0. The last thing is a lot of AP multiple choice questions won't ask you to write like a whole Taylor polynomial. They might just ask you for a coefficient. So if you want a shortcut for the coefficient of the term, meaning what's going to go in front of, say, your x to the nth power or your whatever minus c to the nth power, that's how we get those coefficients. It's going to be our nth derivative over n factorial. So an easy way to find that if you're looking. So what I want to do first is I want to just write a Taylor polynomial given the information about the derivative. So I can't show you this graphically because we don't know what f of x looks like, but I just want to play with the formula itself. Then in our second example, I'm going to have you find some derivatives. And as we go, I'm going to plug in to Desmos so we can see how well this is matching our graph. So this should feel not too bad because I've been doing Taylor series for a long time, so I know the formula well, but there's a lot of patterns to the formula. So notice like that second term here, the one with the squared, we have the second derivative 2 factorial squared. And all of those things, those patterns are going to be helpful as we kind of start to memorize this. So, Taylor polynomial degree 3. Does anyone know what the degree of 3 is going to tell us? Yeah, the biggest one we're going to have is to the third power. What does the centered at 2 tell us? C equals 2. So I'm going to see a bunch of x minus 2s. I'm going to plug in 2 to all of my derivatives, which is really helpful because look at all of those things they've told me. They all have to do with 2. So we're going to answer 2 questions. We're going to write a Taylor polynomial that ends with x cubed and is going to look like x minus 2s all the time. And then we're going to answer what's the coefficient of the third degree term. So I like to write my Taylor polynomials with this notation. It gets used in textbooks a lot. Either a capital P or a capital T. These are approximately equal to our function because we're stopping at some point. Eventually, we'll be able to write these where they're actually equal to our function if we use infinitely many terms. So our first term is f of c. So our first term in this one is 3. Thrilling. Our next term is our derivative times x minus our center. So I'm going to do minus 4 times x minus 2. Now, if I stopped here, technically this is a tangent line. You don't have to write this, but this would be like y minus 3 equals slope x minus 2, add the 3 over. It's just a tangent line. But I'm going to keep going. I want to match more than this just first derivative. I want to match the second derivative. Now, it gets spicy once we get to the second derivative, because then I got to start dividing by factorials. So once I get here, I'm going to do 7 over 2 factorial, x minus 2 squared. So notice, second derivative, 2 factorial squared. All right, the next one, 5 over 3 factorial, x minus 2 cubed. And I'm done. I'm really not going to do much to these things. We're going to learn how to find different things with them later. But for right now, I'm really not going to simplify them. The only thing I would probably do ever to simplify this is called 2 factorial 2 and 3 factorial 6, but that's about it. All right, for the coefficient, anyone think they know what I'm going to write down for the coefficient of the third degree term? Yep, negative 5 over 3 factorial, which is negative 5 over 6. Either one of those is a fine answer. If I ask for the coefficient, though, just a reminder, that should be a number and not have your like x minus 2 cubed in it. I just want the number. Yep. All right, so let's do this with an actual function now. So this is all well and good if they give me all of those derivative pieces of information, but sometimes they won't. Sometimes they'll just give me a function and they'll task me with finding all the derivatives. So what I would like you to do while I get my graph set up on the board, I know f of x is equal to e to the 3x. Can anyone tell me what is the highest power that's going to be in this Taylor polynomial? 4. So I'm going to go up to the 4th power, which means I need how many derivatives? 4. So you're going to find me f prime, f double prime, f triple prime. And what am I going to write instead of f quadruple prime? Does anyone remember the notation? We do, once we get to 4, we do 4 in parentheses. Anyone want to tell me something about this derivative as you take it? What? All right, derivative of e to the x is e to the x. What about the 3x part? Chain rule. All right, while I get my graph set up, I want you guys to find me 4 derivatives and then find your center and plug it into all 4 of those derivatives. So ideally, you'll have a list of derivatives and then you'll be plugging in something to all of them. That should be your center. All right, I don't want a decimal. You can leave it in terms of e. Let's learn together. Thanks, Desmos. All right, let's see if that'll work. Ah! Oh man, he's tall. Oh, he's so tall. Yes. Yes. All right, you guys got 4 derivatives already?
Yeah.
All right, what's my first derivative? 3e to the 3x. Second derivative? Cool. Next derivative? All right. All right, what did I need to plug into all of them? All right. Then, as I plug in, what's this exponent going to turn into? Cool. I chose this example mostly because these numbers don't have to be nice. So just a warning, they don't have to be like nice integer numbers. Usually they will be, but they don't have to be. So I would like to try to write p sub 4 of x. So our 4th degree Taylor polynomial. What I want to do is after every term, I want to flip back over to Desmos and show you what this looks like on the graph. So kind of trying to do what that video was trying to show you as we were moving forward. So what would our first term in our Taylor polynomial be? E to the 6. Now this graph is on a big zoom because e to the 6 is really big. That blue point there is like the point where we're writing this tangent line. So here is our first function, y equals e to the 6. So notice we're matching the y value, but we're not matching anything else. So this is probably not going to do a great job at approximating, but that's fair. We only found one literal term of this guy. All right, what would our next term look like? 3e to the 6 times x minus 2. All right, let me go type that one in to show you what's happening there. So plus 3e 6 times x minus 2. What other words could you use to describe what that is? That's our tangent line. So we're matching the y value and we're matching our first derivative there. So a first degree Taylor polynomial and a tangent line, same thing. So if you want to be obnoxious, ask for a first degree Taylor polynomial instead of a tangent line. Yeah.
Are we gonna have to like solve for the Taylor series?
So we're kind of currently doing that. We're just doing it term by term. All right, what's our next term going to look like? All right, let's Connor was talking quiet. So we're taking our second derivative, the 9e to the 6. Now that we're at our second spot, we're dividing by 2 factorial and doing x minus 2 squared. You could divide each of these by their corresponding factorial since 0 factorial is 1 and 1 factorial is 1 if you want to make sure you don't forget your factorials. All right, I'm going to type that in. 9e to the 6 divided by 2 factorial x minus 2 squared. All right, so we now have a parabola, kind of cool. Also, it looks like this is doing kind of a better job approximating a little bit farther away from that point. We're kind of matching the curvature a little bit more, matching the concavity, if you will. All right, let's continue. We've got 2 more terms. Someone whose name is not Connor, help me out with the next one. Perfect. All right, while I'm typing that one, I want you to write down the next one on your paper. All right, if you want to peek up at the board, this is the term that Brandon just gave me with the cubed. Is it looking like it's doing an even better job approximating? So it looks like those graphs are overlapping. They're not exactly overlapping, but farther and farther away. What would that last term look like? Over what? And then x minus 2 to the 4. All right, this one, honestly, that right-hand side, those graphs look almost exactly the same. So notice we're gaining much better approximations by doing, I would argue, not too much math. So we're getting a lot of accuracy now, even though we haven't done too much in terms of like computational strength. So let's go ahead and finish up here. Looking at the question that I asked, have we answered all parts of this question? No, I was asked for a specific coefficient. That was of the 4th degree term, so I'm going to steal that 81 e to the 6 all over 4 factorial. You could simplify 4 factorial into a number, or you could leave it as is. Hello. Not right now. All right. So, yeah, that's her. She knows more than I do. Definitely. Or DM the outreach remind. All right. So really all we're doing is just creating these right now. I want to give you big picture though. Eventually, did anyone find this process annoying, just taking 4 derivatives and plugging into a formula? A little bit. There are going to be other ways to make things like this. So we're going to spend a lot of time this unit trying to figure out other ways to do this, because doing this process is annoying. So let me ask you to do it. I would like you to find me the Maclaurin polynomial for n equals 5 for sine x. All right, tell me anything you know based on those directions. All right. Our Scottish friend tells us our center is 0, which is nice. That means we don't have x minus the centers to powers. We just have x to powers. What the heck does this mean? All right, the 5th degree is the fancy way to say it. Thanks, Ashley. That essentially just means that my last power should be 5. So you're going to start by finding me 5 derivatives, plugging in 0 to all of them, and then writing out your terms. I want you to practice with this. I will put the formula back up on the board if you don't want to flip back and forth. But I'm going to give you probably about, let's take about not 25 minutes. Let's take about 4 to start it, and then I'm going to start putting up my work. So find me 5 derivatives, and then you're going to start finding my Taylor polynomial at the 5th degree.
Sorry. So again, maybe we'll get it down eventually. Hopefully by the that would be positive. Okay, let's see if we got
Oh, also this is our second to last unit. Can you read it?
that's a total.
Wait, what time are we?
Right around spring break. I think I'm gonna have to finish up polar after spring break. But
What was the day?
April 11th is the start.
Like 1 month. Wow, you have to.
Yeah.
Yes, we're almost done learning.
What's the derivative?
Officially employed again, starting this weekend.
Wow.
2 months ago, just really.
Time is
You're right.
No,
It's starting to wire, yes. I always If I was to forget that I was saying around 4 and the 5 and the derivative would knock me points off for notation. Because I just like skip it, but then I have to go back and have
And then that becomes
That's probably
regular
the
sine.
looking at.
Okay.
Cycle begins
So they only pull one.
Yeah.
Not all.
on and
Like
they
some of them are
love
negative.
craft.
Wait, so sine goes
Some of them are.
Then it goes to negative sine.
Zero.
Negative sine.
goes,
And then
which goes
negative
to sine.
Zero.
Yes.
Okay.
Yeah.
I need to make sure my units are really hard.
It's supposed to be the other
Like negative sine of 0. Negative 0 doesn't make sense, so it's just. Oh, wait, 0? No, because it was sine of negative 1. I'm just not in circle, but no.
I don't remember. Man.
It's right in the middle of that.
That is like, I remember we had to write the entire unit. That wasn't bad. We were working on it.
Just regular.
Now go to first doing it out.
Oh, I ran out of space.
All right, once you have your derivatives, try plugging in your zero, your center for Maclaurin. And if you're feeling spicy, try to write that Maclaurin polynomial. I'm going to start writing some of my derivatives because I'm getting bored. Hello. All right, help me out with some of these things. What is sine of 0? I'm going to ask that one more time. I better hear the same number from everyone. What is sine of 0? What's cosine of 0? What's negative sine of 0? Negative cosine of 0. Next one. Cool. All right, so as I write out this Taylor polynomial, notice that some of the terms are getting kind of killed off here. So at the end, I don't really want to write the terms of my Taylor polynomial that are 0. I kind of want to leave those out. So we're going to do p sub 5 of x equals. All right, will I have a constant term? Will I have one without any x's in it? It would be 0, but I'm not going to write it because 0 plus anything, I don't care. All right, so the next term is going to be our x term. It's going to be 1 times x. So I'm going to write x. All right. Will I have a term that has a squared in it? No, because I have a 0 for my second derivative. So I'll have a term with x cubed in it. What's that term going to look like? Perfect. Yep, I'm skipping the ones that equal 0. So this would be like 0 plus. Yeah, so eventually this is one of the ones that we are going to memorize. So we're going to want to have this memorized in its simplest form. So you're not wrong if you're writing the plus zeros. We're just going to write it a little bit cleaner. All right. Will I have one that has an x to the 4th on it? No, because I'd have 0 over 4 factorial x to the 4th. What's my last term of this 5th degree Taylor going to be? All right, now, here's the fun part. We're eventually going to memorize this one, so I just want to play for a second. Do you think I would have a 6th degree one? Do you think I would have a 10th degree one? What do you think the next term of this Taylor series would be? All right, do you think it would be positive or negative? You're right. Cool. So eventually we're going to memorize this one. What do you think the cosine one would look like? What do you mean?
Like, it'll be 4 and 6.
It'll be all the even ones. Nice, Michael. So there will be patterns as we go to multiply these or as we go to kind of figure them out. So does everyone have a calculator on your desk? All right, I want to play a little bit with error. So if you don't have a calculator, they're behind Austin. He can chuck one at you. Good catch. Oh, okay. Austin, if you're going to chuck, you got to chuck better. All right. So what I want to do, as Austin is checking calculators, I would like to give you some instructions. I'm going to have you guys kind of finish out the page, but I want to give you some directions. So what you're going to do is you're going to plug in some numbers to our polynomial and our numbers to our function. So first of all, we're dealing with trig, so everyone go to mode and make sure you're in radians. All right, what I would like you to do is I would like you to plug in 2 numbers, both to the polynomial and your function. So for p sub 5 of 1.4, you're going to go over to that blue function right there, and you're going to plug in 1.4 to x. If you're asking me how to plug in the factorial, what I would do is just figure out what 3 factorial and 5 factorial are and use those numbers instead. There is a factorial in the calculator. I don't know where it is. All right, then you're going to plug in 1.4 to sine x. You're going to subtract those 2 to find the error. Then you're going to do the same thing with 2.1, and then I want you to think about the questions at the end of this. So you're trying to fill out the rest of the page. I'm going to give you about 4 minutes to try to fill out the rest of this page. Yeah, that's fine. Yeah. You just gotta put you gotta put
120. I got there.
Yeah, so you just want to put straight. So if you are confused on directions, I'm going to show you what I want you to do on the board. I just want you to plug in 1.4. If you're really confused, find the middle column, find sine of 1.4 and sine of 2.1, the middle row. Alpha y equals. All right. So 1.4 plus. That's what I was gonna do.
You want to know where it is or something?
No.
Okay.
Okay. See, because I knew it was going to be complicated like that. I also forgot my minus. You're just plugging in 1.4, y'all. Not hard. Plus alpha. Thank you for that information. Did you check that you were in degrees?
In degrees or
Radian, sorry. I bet you didn't use parentheses around your denominator. All right, so this is what I'm looking for you to do. So notice I plugged in 1.4 to the top, 1.4 to the sign, and then I subtracted the 2. So that's what I'm looking for. So hopefully if you didn't do that first one, you can do the next one.
Another way to do it.
Whatever you want. Mostly I'm trying to make a point about how close our approximation is. This is not something I would probably ask you to do. This is more of a learning moment here. I'm doing it for the learning moment, y'all. All right, so what I want you to notice, and if we're having problems plugging in, I can steal decimals from someone else. How good was our approximation? Pretty dang good. Almost good enough that we would get this question right on the AP test if we approximated using this thing. We're close to being within 3 decimal places of this guy. I would argue in the grand scheme of making an approximation and the amount of math that we did, you guys got this done in about 4 minutes and we were within 3 decimal places. That's pretty darn powerful in terms of making an approximation. If you think about making a computer do this, that's a very quick calculation for a computer to do to get with a very high level of accuracy. Did anyone do the 2.1 ones? All right, I'm going to roll with the whole decimal just to make a point here. Now, if you did do this, or if you're just looking at these now, which one was better? Which one had a better error? Which one had a worse error? More so like, which one had a bigger error? The second one? Why do you think that is? What do you mean it's a bigger number?
I don't know.
All right. So let me ask you a question. Let's go back to our graph. I'll home screen myself. What was our function that we were doing? All right. Here is our Taylor, x minus 1, 3 factorial x cubed. Where did we center our polynomial? 0. Our first approximation was that x is 1.4. Our next approximation was at x at 2.1. Which one's farther away from our center? 2.1. So in general, usually the farther we are from our center, the worse our approximation. I say in general because we don't know what our functions are doing, but we're getting a pretty good idea of how far this guy is good for. All right, so here the error is larger. So what do you think would happen if we use this to estimate sine of 2.7? Yeah, probably even bigger. 4. Go away. All right, what time is it? 48. All right, I think what I'm going to do is I'm going to save the rest of this for later, and that's fine. It doesn't take that long. Yeah, error. Nope, you're good. That's probably better of me. So we're going to finish this up later. Does anyone think, just off the top of your head, does anyone want a better explanation of like why the factorials are there, where this formula comes from? Do you care algebraically why the formula is the way it is? Yeah. not for the chain rule. It's more there for, let me see if I can click. It's more there for the derivatives. So essentially what happens is when you power rule this down, the first time you take the derivative, you would get a 4, then a 3, then a 2, then a 1. So to counteract that, is that what you meant? Okay. That's to counteract that. So that's why you have those integers there with the factorial kind of collecting all of that. If you're super interested, I think this video does an absolutely fantastic job walking you through the whole thing. It is 20 minutes long, so I didn't want to take all of that time. But very fantastic. If you want me to do a separate explanation, I have all of it typed up and ready to go. I'm more than happy to give you a further explanation. But really, the general gist is you're trying to match each derivative term by term, and the structure of this allows you to do that. Yeah, Michael.
How many notes are in this?
5. Yep. So looking at what we have to go, I'll kind of pull up the titles of everything. There's 5 sections in unit, what the heck unit are we in? 9. They have these names. Taylor polynomials is what we did. We'll finish that next time. This was me looking at the notes from the end. Interval of convergence, that's the one where we kind of find something using ratio tests. So ratio tests will make a big reappearance in interval of convergence. Taylor series and power series are kind of how to get around doing this without taking a million derivatives. And then big boy, Lagrange error bound. This is probably one of the hardest things we do because that's the formula. So it's like, what the heck is that? So that's talking about how far are we off? If we stop our approximation at 6 terms, how far are we off from the actual thing? These are last year's notes. So this is what we'll be talking about. It is a weird process and the formula is really big, but it's not that scary once we get enough practice in. Yeah, we talked about alternating series error bound. So those will actually compare the two a lot. All right, before we end today, remind me, what's happening next class? Unit 8 test. All right, no, we don't have time for that, y'all. I do. All right, so if you want to review, I'll drop some paper on your desk. So as a reminder, the way I would review for this test, please make sure, one, that you know the conclusions for the test. So if you're doing ratio tests, you get greater than or go to class. Then go to lunch. You're not here. This is my class. Go away. All right. If you are studying for this test, 1, make sure you know the conclusions for the test, but 2, make sure you have a general idea about what tests are good for what type of series. What you'd want to avoid is having to redo an entire problem from start to finish. So even if you're not going to go and do all of the problems on the review, highly recommend maybe go through and just see if you know which test to use for which thing. If you want more practice for anything, I can certainly find some more. Again, these flow charts can be a little helpful if you're trying to decide what tests to use for what. Just ignore the Taylor series on this one or go Harry Potter on this one. All right. Any other further questions before we roll? All right. So test next class. If you don't want this review, feel free to just leave it on your desk. If you are still missing your quiz, come take your quiz. I may just make you take your quiz next time while you take your test. Double it up. All couches, all the time.
Yeah.
On one note, and oh, I have more time. No. Oh my goodness. No, I have way more time. Pull out those notes. No, I forgot it was advisory day. Pull your notes out. Pull your notes out. Pull your notes out. We are not done. No. I have 10 minutes. Oh, excellent. All right, pull those notes back out. Yeah.
Why must you sacrifice your morals?
think everyone in here knew that.
You didn't tell me. I thought I was done.
No, you said you had 3
No,
minutes
it was just.
I don't know what he's doing. Let's do this page. All right. So let's figure out how we can use Taylor polynomials now that everyone is looking at me like I just killed a puppy. All right. So I am, because I like Taylor. It's really fun. All right. Let's go ahead and look at this guy. So we have a second degree Taylor polynomial. What's the center of this guy? 0. Let's talk about why I know it's 0. 1, they say about x equals 0. It's another way to say centered at 0. Also, looking at that polynomial, how do you know the center is 0? Yeah, just the x, right? We don't see x minus the center. We just see x. So we have x there, x squared. If it wasn't 0, would they actually give us x? Yep, we're always going to keep it in that form. So whatever we see x minus that, we're never going to take like this guy that we did. We are never going to multiply that out. You want to see the center in there. All right. So looking at this guy, let's talk about A, B, and C. So this is very much like the one they set up in that video. So A, how do we get that first term? What do we normally put there? Yep, our f of whatever, f of the center, so f of 0. This is a graph of f of x. So what could you tell me? We're looking for the signs. Could you tell me anything about the sign of f of 0? How do you know it's positive? Yeah, we're looking at the y value. This is above the x-axis. Crazy. All right, how do we normally get the thing in front of x? All right, let's look. The thing in front of x is our f prime, which, Connor, you were just reminding us what f prime is on the graph. The slope. Oh, it's a positive slope? So this is greater than 0. All right, how do we normally get the thing that goes in front of x squared? Second derivative. And what is it usually over? I feel like it was in a fraction. 2 factorial. Doesn't really matter when I'm finding the sign, but what does the second derivative normally tell me on the graph? Concavity. What is this concavity? It's concave down. So this is negative. So look at how cool these questions can be. I can connect them to a hecton of other calculus concepts. All right. Oh, yeah, it's super fun. All right, let's try this guy. All right. Looking at the next question, we now have a Taylor polynomial, and they're asking us to kind of go backwards to try to figure out what these terms are. So I have centered at x equals 4. So notice, kind of like Brandon was asking, are they always going to keep those x minus 4s? Yeah, I can see them. They say x minus 4. They're not going to be multiplied out. All right, anyone want to give me a solid guess, not what f prime, what f of 4 is based off of that, Taylor? 2, crushed it. All right, anyone got a solid idea of what f prime of 4 is? Ooh, close. Ooh, 0. Does anyone see that there's no x minus 4 to the first power term? 0. There's no linear term. Ooh, all right. So f double prime of 4. Why is this not exactly equal to negative 5? I'm going to tell you that is not true. This guy should be over 2 factorial to get negative 5. All right, so remember, to get these numbers, once we get to square, this is f double prime over 2 factorial. So what is f double prime of 4? Negative 5 times 2 factorial, or negative 10. All right, f triple prime over what? Has to equal 8, which means f triple prime of 3 factorial is, give me a number. 48. 3 factorial is 6 from 3 times 2 times 1 times 8 is 48. So very crafty and clever and weird. What? Forced. Oh, because I did a typo in my brain.
Oh,
Thank you, James.
okay.
I appreciate that. Sometimes when I'm talking and writing, it's hard. All right, so last little connection piece, and then I promise I'll be done. I won't lie this time. Here's another cool way I can connect. So these words don't look like Taylor series words. Does F have a local max, a local min, or neither? That's like AB words. All right. What do I need to know to find a local max or a local min? All right. So I need to change in slope, but I only have so much information. How do we normally find a max or a min? What do you usually do first? What? Critical values. All right. Do I have a critical value? That's fine. Steal his answers. How do we know if we have a critical value? If what's 0? Which, all right, if f prime of that value, which is 4, should equal 0, does it? Yes. Cool, we have a critical value. Now, do we have enough information to make a sign chart? No, we only have certain pieces of information. So y'all remember, dig deep back in your brain, the second derivative test. All right. Let's see if we can remember. What do you know about the second derivative based on the stuff we did in part A? It's -10. Why do you think I care about that number? Okay. What does a negative second derivative normally tell you? Oh, great. Awesome. All right. Concave down, flat slope. Based on my picture, can you answer the question? Yeah. So we can say local max because f prime of 4 is 0 and f double prime of 4 is less than 0. Why am I pulling really old stuff back into the game? You are what? Fair. A good way to review for the AP test. Also, you are essentially guaranteed a free response question on Taylor series. We'll do a bunch of them. But this is one where you're going to just want to chuck stuff at the wall. The Taylor series questions tend to be harder, meaning the average points on them is lower. I think the material is accessible, and you guys will be able to do it, but we're going to have to practice because they can connect a lot of stuff back. All right, so I promise I'm done now. We'll review with the back part when we come back in 2 classes. Why won't we be learning next class? There's a test, because you're welcome. I'm just going to ruin Wellness Wednesday. You're welcome. Yeah. Sparkle trivia. Dual multitask, probably. Yeah, if anyone just wants to review for the test, you can sign up for my Wellness Wednesday. I won't bother you. Mine is like Sporkle trivia.
Sporkle Coach Campbell made us play at a pasta party like 4 years.
There's a lot of different ones that aren't super challenging. Yeah. You want me to just give it to you and you can just walk with it?
Oh, will your parents be? Do you want the? This really is exactly like. If you change.
I would change your sign up because they're probably going to take attendance. Maybe email Coops?